Okay, let's look at 82. It says the rate of change of the altitude of a hot air balloon is given by R of t. Which of the following expression gives the change in altitude during the time that the altitude is decreasing? Okay, one thing we have to recognize is R of t is the rate of change of altitude. So it's not the altitude value itself, it's the rate of change of altitude. So the value that we get back in return is, for example, it's feet per second or meters per hour. It's not going to be just feet or just meters. So essentially we're looking at the derivative function. So what we can do is we can graph this in the calculator and identify some important points here. So here's my R of t function. Whatever is above the x-axis indicates where the altitude is increasing. Whatever below is where the altitude is decreasing, because my R of t function represents the rate of change of altitude. So we can use our calculator feature to find the zero. So if we do second trace 0, we can find these x-intercepts. These x-intercepts is at 1.572 and at 3.514. So if we accumulate the depth integral from 1.57 to 3.514, we can figure out the total change in altitude during the time when altitude is decreasing. So we know that this entire time the hot air balloon is going to be decreasing in altitude. So if you accumulate all those rates of change, we can have a value that represents the total altitude that the balloon drops, whether it's in feet or meters. So the accumulation of RT from 1.5 to 3.514 will get us that value. Okay, 83. The velocity is moving along the x-axis given by v of t. What is the average velocity from 0 to 3 seconds? Now, if we want to find the average velocity and if we have the velocity function, we're going to use the average value theorem. Average value theorem will help us find the average velocity. The formula is 1 over b minus a, integral from a to b of v of t dt. Our a and b values are 0 and 3, so I'm just going to plug in 3 in for b, 0 in for a. Depth integral from 0 to 3 of e of t plus te to the t dt. Now in your calculator you're going to be using x's, so you're going to say e to the x plus x e to the x. Find the accumulation of velocity divided by 3, we have our average velocity, and our units of measure is feet per second. Okay, 84. A pizza is heated to a temperature of 350 degrees Fahrenheit, taken out of the oven and placed in a 75-degree room temperature at 0 minutes. The temperature is changing at a rate of negative 110 e to the negative 0.4 t degrees Fahrenheit per minute. To the nearest degree, what's the temperature of the pizza at time t equals 5? So this 350 is not going to be, so this 350 degrees is telling us how much, what the temperature is at t equals 0. So we can gather some information here. We know at time t equals 0, our temperature of the pizza, the pizza is going to be 350 degrees. And in the end, we're trying to figure out what is the temperature at time t equals 5. Okay, so that's the unknown we're looking for. Looking for the temperature 5 minutes after it's been taken out. So the equation or the function given to us, the expression given to us, is a rate of temperature. It's not the temperature itself, it's the rate of change of temperature. So we're going to call that P prime. So P prime is negative 110 e to the negative 0.4 t. I'm trying to get to our position function, our temperature function, pizza temperature function, so that we can use these ordered pairs. So I'm going to represent P prime as dp over dt. And if I find the antiderivative of p prime, it'll bring us up to a p of t function. So if I want to find the antiderivative, I have to apply the rule for e to the u, and the rule for e to the u is e to the u plus c. But our u value is more than just an x, or more than just a variable, is negative 0.4 t. So that's our u value. Our u value is negative 0.4 t. du dt is equal to negative 0.4. We solve for dt, we get du over negative 0.4. We make that substitution. And once we make that substitution, we can push all the coefficients out in front. That coefficient just becomes 275. Integral of 275 e to the u is just going to be e to the u plus c. The coefficient stays. And once we have our p of t, or our temperature equation, well, I'm going to replace the u back in terms of t. And I'm going to solve for c. So to solve for c, I'm going to plug 0 in for t, 350 in for p, and 350 equals 275 plus c, so c is equal to 75 after I subtract 275 from both sides. So that updates my general temperature equation to a specific temperature equation. Now I have this information, I can solve for, figure out the temperature of the pizza at 5 minutes in. So plug 5 in for t, use the calculator to simplify, and we get this reduces down to 112 degrees Fahrenheit. Answer choice A. Okay, 85. If the trapezoidal sum approximates the definite integral from 0 to 4 of f of x dx, and a right Riemann sum under approximates it, which of the following could be the graph of f? So we want to find a graph that will have an under approximation for right Riemann sum, but an over approximation for trapezoid. And the only one that's going to fit that bill is going to be option A, the graph of A. So let's show why that's the case. If I were to create a right Riemann sum, that means I'm connecting the right endpoint of each subinterval to the graph and letting that be the height. We see that if I draw all these right-handed rectangles, these rectangles all sit below the curve. So the areas of these rectangles added up is going to be less than the areas of this curve between the curve and the x-axis. So we know right Riemann sum is going to under approximate the area. Now the same graph is going to have a trapezoidal over approximation, because it's hard, maybe it's hard to see here, but these trapezoids are going to be slightly above, peaking above the curve. So the areas of these trapezoids is going to be slightly greater than the actual area between the curve and the x-axis. So we say the trapezoidal sum over approximates. This is the only curve that will allow both of these to be true. So it doesn't hold true for these other graphs.